So welcome back students. Last class we have discussed on shear force and bending moment diagram during the offline class. We have done the case of cantilever beam and simply supported beam. Now we are going to move on to the next question, that is question number 12, to simply supported beam with overhang. So as you can see, this is a case of a simply supported beam with one side overhang. So as we say, we will start the session. We will need to run a section from either left end or right end. For the convenience and for the uniformity, we will start the section from here. And so we need to mark the change points. So I can mark here this is A, this I will mark as B, and another point that is C. As in the case of a simply supported beam, we need to find the reaction at A and B, that is RA and RB. So when we find the reaction at A and B, we will get RA plus RB, that is when we take sigma B is equal to 0, we will get RA plus RB is minus 10 is equal to 0, which means RA plus RB is equal to 10. Now taking moment about any point, I will take about sigma M about A, I will get first 10 into 10 meter in the clockwise direction minus RB into A is equal to 0. From here I will get the value for RB as 12.5 kilonewton and RA as minus 2.5 kilonewton. So this minus 2.5 implies whatever direction we have assumed here is not correct, or it is opposite to the direction we have assumed. So the real direction of this particular reaction RA force is actually coming in this form. It will be in this direction. RA I could mark it as this, and I can mark this one as 2.5 kilonewton, and this will be 12.5 kilonewton in the upward direction. Now once you solve this, now we will need to go to our drawing the shear force and bending moment diagram. We will start with the first case, that is the shear force diagram. First one is the section is over here, that is left of A. The section is towards the left of A, and C, I can say the shear force is 0. So I can write the shear force at A is 0 for the first case. Now your section has moved towards the right of A and you are looking towards the left. You have an unbalanced force of 2.5 kilonewton towards the downward direction. Since you know our sign convention is, we have taken this as positive and the other one to this as negative. So you could see here my section is here and it is towards the downward direction, which means I need to consider this one. So this is minus SF at A, just towards the left I can take it as SF at A is equal to minus 2.5 kilonewton based on the sign convention. Now your section is moving from here to this point, and it reaches just to left of A, and when I look towards the left side, we could see there is only one unbalanced force, that is minus 2.5 kilonewton. Again I can write SF at B just to the left is minus 2.5 kilonewton. Now the section just move towards here. Either I can look towards this direction or I can look towards this direction, which is convenient, you can see. But if I look towards the right direction, you could see there is only one force. But if I look to the left direction, there is two forces. So it's up to you, whatever be. But I will consider SF at B, and I am looking towards the right, which is my easier portion. I am looking towards the right. There is a 10 kilonewton in the downward direction. That is, there is a 10 kilonewton which you could see that is in the downward direction. I will take it as positive. So that is SF at B, I can take it as 10 kilonewton towards the downward direction. Now your section now moves towards here, just to the left of C, and it is looking to the right. You could see there is another 10 kilonewton. So I can write there is SF at C, I can write as 10 kilonewton towards the right. Now your section comes over here, you are looking towards the right. We have SF at C as 0. So that completes the shear force diagram. Now you could see, we will draw the variation of this. SF at A is 0. At the same time there is minus 2.5. That is, I can write it as minus 2.5. I'll take it as negative. This is the case of SFB. Now it goes from here to here. There is no load. From here to here, there is no loading, which means your shear force will be a straight line, which means I can write this one will be a straight line, and at this point you will be having 2.5 as your value for SFB. But at the same time, here your shear force value will increase to a value of 10. So at the same time it will increase to a value of 10, that is plus 10, to become 10. Again, from this point to this point there is no variation, and over here you have there is no variation, so it will be a straight line, and at this point again you have 10 and this 20. So this will be total positive and this will be total negative. Similarly, if I want to draw the shear bending moment diagram, we have bending moment. You can straight away say the bending moment at the end points, that is bending moment at A is equal to 0, as well as the bending moment at C is equal to 0. Because if you have a section over here, there is no loading towards the left, you can say the bending moment is 0. The section is over here, there is no loading towards the right, the section is 0. So you have the bending moment pertain to this point, that is B. So you need to find the value for bending moment at B. That is, I need to consider a section here. I can look either to the left or I can look to the right. I'll look to either of the direction. You can just see whether it is correct or not. So first I'll look to the bending moment at B. You can see bending moment, I am standing here and looking towards the left. There is a 2.5 kilonewton in the downward direction. So as you know, the sign convention for bending moment, we are taking sagging as positive, and hogging as negative. So you could see here, you are standing here, there is a downward force here, which means you are standing here, there is a downward force. This is a pure case of a hogging moment. So I can say there is a hogging moment, that is negative moment, 2.5 into H, that is 20 kilonewton meter. A negative moment is acting at B. And if you see towards the right also, if I am taking towards the right, there is a 10 into 2. There is I am standing here, there is a downward force which makes it negative. A 10 into 2, that is minus 20 kilonewton force in the downward direction. So I can mark this one as bending moment at B is either minus 2.5 into H or minus 10 into 2, which makes it minus 20 kilonewton meter. So if I draw the variation for this, you could see this is a bending moment diagram variation. You could see at A it is 0, at B it is 0. So at C it is 0, so it is 0, 0. At B you have a value of minus 20 kilonewton meter. And you could see from C to B and B to C there is no loading. So your bending moment variation will be a linear variation like this. That is, a first degree curve will be your bending moment variation. So you could get your curve like this. The whole will be negative. I hope you understood this. So now we have the next question, question number 13. If you have a overhanging beam with a UDL of 20 kilonewton meter for a 2 meter distance and a 6 kilonewton at the free end. So if you take the reaction part solving, you will get the value for your reaction RA. Say this is the change points. I can say this is A, this is B, the end of the UDL, another point C and D. So you get the value for your RA as 27 kilonewton and your RC as 19 kilonewton, the support reaction. So I can mark this one as 27 kilonewton and this as 19 kilonewton. So first I will draw the variation of shear force. So if you draw the variation of your shear force, we have the change points over here. So all these points we need to draw the variation. So shear force at A, that is your section is over here. You want to find the shear force at A. Is at A, I can write it as 0. Now your section is moved towards here, looking towards the left. There is a upward force of 27 kilonewton, which makes it positive 27. That is SF at A, I can write it as 27 kilonewton. Now your section will move towards this point, and you could see your section is at B, and here I can write the shear force as BS. If you stand here, there is a upward force of 27 kN, which makes it positive 27, and a downward force of 20 kN per meter for a 2 meter distance, which makes it negative. That is, you can write this one as 27 minus 20 into 2, which makes it 54 minus 40, that is minus 30 kN. Now your section is over here. You could see the shear force at C. It is the same value, that is 27 minus 20 into 2, that is minus 13 kN. Now your section has moved towards here. You are looking towards the right. There is a downward force of 6 kN. That is, downward force means 6 kN. It is positive, so that I can write SF at C again. It is 6 kN. SF at D also I can write it as, standing here looking towards the right, there is a downward force, so it will be 6 kN, and SF at D at the end it will be 0 kN. So if you plot the variation, you could see there is 0 over here. At the same time there is a plus 27. So this is 27 kN. This is SF 27 kN. From B to C you have a UDL, which means it will be a linear variation. And at B you have the value as minus 13 kN. So it means it will be minus 13, it will be somewhere here. And the variation is a linear variation, so it will be minus 13 kN over here. That is 13 kN. Now from B to C there is no load, so your shear force will be a straight line. So it will be a straight line like this. So it will be 13 kN itself. As you can see, there is 13 kN here. Now at C there is a hike in your shear force value. It moves to 6 kN. There is 6 kN over here. And between C and D there is no load. As a result, it will be a straight line. See, that is 6 kN, and this crosses your shear force diagram. So it will be positive, it will be negative, it will be negative. So this will be positive. This is the case of your shear force diagram. Similarly, we will draw the bending moment diagram. You could see the bending moment diagram for the case bending moment. I can straight away write bending moment at A is equal to 0 and bending moment at D is equal to 0. Now I need to find the bending moment at B and C. So if you see the bending moment at B is equal to what? I am standing here, the section is towards the left. There is a 27 kN meter in the upward direction, which makes it positive, and 20 kN per meter in the downward direction for 2 meter, which makes it negative. So if I write here, this is 27 into 2 minus 20 into 2, that is the UDL, into the distance 2 by 2. 54 minus 40, it makes it 14 kN meter. Now you need to find the value for bending moment at C. Your section is over here. You need to find the bending moment. I will take the easier one, that is 6 kN towards the right. You can see there is a 6 kN towards the right in the downward direction, which makes it a negative value. So you can write this one as bending moment at C is equal to minus 6 into 2, which is minus 12 kN. So if I draw the variation, this is your BMD. At A it is 0, at A it is 0, at C, D also it is 0. In between B to C you have this value as plus 14. So this is 14 kN meter, and at C you have this value as minus 12 kN meter, that is 12 kN meter over this point. So from here to here, you know the variation from A to B, your variation will be a parabolic second degree variation, and B to C I could mark it as what? It will be a linear variation. So I will mark it like this. From A to B it will be a parabolic variation. From here to here it will be a linear variation like this, and at D point again a linear variation goes to like this. So this is 0, this is 0. As you know, the peak value of bending moment will occur at the point where the shear force is 0. So I need to find where this shear force becomes 0. So correspondingly, I need to find the value for my bending moment also. So you could see I'll consider this shear force 0 is between span A to B. So what I do is I'll consider a section here. I'll consider a section where your shear force has become 0. I'll consider the section XX where your shear force is 0. So if I draw the variation here, you could see my loading diagram will become like this. That is, at this point there is a UDL 20 kilonewton per meter for X distance, and this is 27 kilonewton. This is your XX. I can write the general equation for your shear force at XX. That is S at XX. I can write it as what? 27 in the upward direction, which makes it plus 27 minus 20 into X, which means that is, I can say that is equal to 0, which means X is equal to 27 by 20. 1.35 meter from support A. So your bending moment shear force becomes 0 at 1.35 meter, and your bending moment value will be maximum at that point. So I need to find again the value for your bending moment at 1.35 meter from A, which means I can write the section is over here. Section is over here, 1.35 meter from A. That is, I can write this is 27 into 1.35 minus 20 into 1.35 into 1.35 divided by 2. So that value I get as 18.225 kilonewton meter. So which means this value is 18.225 kilonewton meter, the maximum value for your bending moment. So wherever there is a change in your shear force, your maximum value for bending moment was there, and there you need to find the value using this method. I hope you understood this. So once you have done this question, you have an assignment question from this topic which you need to submit at the end of today's class. So that will be this question. I will hold I'll create an assignment part in the ET lab to evaluate your class assessment. This is just a class assessment, not an assignment. Based on this only, your attendance will be recorded. You can submit it before tomorrow's class. Thank you.